This video discusses more on functions. We have increasing functions on an open interval. X increases as Y increases, so that means the graph rises from left to right. Decreasing functions, we look at an open interval, X increases and Y decreases, so that means it falls from left to right. And then when you're looking at your function being constant on an open interval, that means when X increases, Y stays the same. So if you look at our first example, we want to state the intervals in which the function is increasing, decreasing, or constant. We are always looking at our x values in order to establish what our intervals are. Remember, we're reading the graph from left to right. We're talking about when x increases, what does y do? So when we look at our first example, we come from negative infinity to 0. From negative infinity to 0, it's decreasing. All right. Then it's going up from 0 to 2. Remember, we're looking at the x and how our graph is moving from left to right. So from 0 to 2, it's increasing. Then from 2 to infinity, it is decreasing. All right, so once again, the graph is going down or falling from negative infinity to 0. Then the graph rises from 0 to 2. Then the graph falls again from 2 to infinity. Looking at the next one, the graph is increasing from negative infinity to negative 3. Then from negative 3 to 3, it's constant. Then from positive 3 to infinity, it's decreasing. The graph is falling. Relative max is the largest or the maximum value on an open interval. Relative minimum is the minimum or the smallest value in an open interval. So it's the minimum or the maximum relative to an interval. Sometimes local is used instead of relative, so a local max or a local min. So if I have this example right here, notice we have our lowest value is negative infinity, our highest value is positive infinity. So we don't actually have a maximum or a minimum for this function, but we can have a local maximum or a local minimum. And these vertexes or apexes of these humps or hills, these curves, they would be your relative maxes or relative mins. All right, so symmetric, being symmetric with respect to the y-axis, it says for every point x and y, there is a point that is negative x, y. And so the way we would test for symmetry to the y-axis, we would take negative x and plug it in for x to see if we get the original equation. Symmetric with respect to x-axis, for every point of xy, there's a point that is x negative y. So the way we would figure out if we have a function that's symmetric with respect to the x-axis, we plug in negative y for y and see if we get the original equation. Then symmetric to, with respect to the origin, for every point xy, excuse me, we have a point negative x, negative y. So in this case, the test is for symmetry with respect to the origin. We will plug in negative x and negative y and see if we get the original equation. So once again, you plug in those values for the x and y to see if you get the original equation. If after your substitution and you simplify, you do not get the original equation, it is not symmetric to whichever test you're trying to prove. So it is possible to be symmetric to the x-axis and not to be symmetric to the y-axis. So let's try this out. So we have the function here, x equal to y squared minus 1. And we want to know whether it is symmetric with respect to the y-axis, x-axis, or the origin. So to test to see if it's symmetric to the y-axis, we will plug in negative x for x and then simplify. So I'll plug in negative x, that'll be negative x equal to y squared minus 1. If I were to take the negative to the other side of your equations to solve for x, I have x equal to negative y squared plus 1. That is not my original equation, so it is not symmetric to the y-axis. All right, to see if it's symmetric to the x-axis, you plug in negative y for y. When you plug in negative y, you have x equal negative y squared minus 1. That negative y squared will simplify to y squared. So I have x equal to y squared minus 1, which is my original equation. So that means it is symmetric with respect to the x-axis. Then to test to see if it's symmetric with respect to the origin, you plug in negative x and negative y and see what you end up getting. Once you simplify, you have x equal to negative y squared plus 1. And that's not your original equation, so it's not symmetric with respect to the origin. Even functions. If you have an even function, when you plug in negative x into the function, you get your original equation. If you have an odd function, when you plug in negative x into your function, all of your signs will be different or opposite of your original equation. So let's determine if our function is even, odd, or even. So we have f of x is equal to x cubed minus 6x. When you plug in negative x into x cubed and to 6x. So don't forget, when you go back up here, look at this note that I have. Whenever you're plugging a negative into an even exponent, that negative is going to reduce and be removed. And so if I have negative x squared, that will be just leave me with x squared. But if I plug in that negative x into an odd function, I will still have that negative left. So going back down here, negative x cubed will leave me with negative x cubed. And then negative 6 times negative x will be positive 6x. So when I look at what I have, each one of my signs are opposite what I originally had. So that means my function is odd for this first one. So the next one, plug in negative x. That would be negative x to the 4th minus 2 negative x squared. When I reduce those even powers, the negatives will be removed completely. And that leaves me with x to the 4th minus 2x squared, which is my original equation. So that function is even. For the final one, h of x is equal to x squared plus 2x plus 1. Plug in negative x. That will be negative x squared plus 2 times negative x plus 1. The negative x squared will remove my negative, but I will still be left with negative 2x and plus 1. So this function is neither, because it's not my original equation, and neither are all of my signs completely opposite of what I originally had. So that would be neither. All right, last thing in this section, we're looking at the difference quotient. This is something that you use more so in calculus, but they do introduce it in this section. So let's look at it. We have f of x plus h minus f of x over h, when h is not equal to 0. So we want to find the difference quotient of f of x is equal to 2x cubed minus x plus 3. So the first thing we do is find f of x plus h. We know what f of x is. We don't know what f of x plus h is. So take x plus h, plug it into your function. We have 2 times x plus h squared minus x plus h plus 3. So don't forget x plus h squared is x plus h times x plus h. Do your binomial distribution. That will leave you with x squared plus 2xh plus h squared. We're going to multiply that times 2. And then also we're going to distribute negative into x plus h. So that'll give you 2x squared plus 4xh plus 2h squared minus x minus h plus 3. That will be my complete f of x plus h expansion. So plug it all into your formula now, your difference quotient formula. 2x squared plus 4xh plus 2h squared minus x minus h plus 3 minus the quantity of 2x squared minus x plus 3 over h. Distribute that negative, so all of those signs will change, and then you will be able to cancel out some terms. So 2x squared minus 2x squared will cancel, negative x and plus x will cancel, and then 3 and negative 3 will cancel, leaving you with 4xh plus 2h squared minus h. Each term that's left should have h left in it. So notice each one of my terms have h. So now to reduce, that h that's in the bottom has to go into each term. So that's 4xh over h plus 2h squared over h minus h over h. Now completely simplify that, and you're left with 4x plus 2h minus 1. And that will be your difference quotient. Once you get into calculus, you will know what to do with this phrase or this algebraic expression. But for this section, this is all they ask of you, and you're done. Let me know if you have any questions.